Okay. Okay. Thank you.
Okay, I would. So if you look at the homework, okay, I did question number 5 posted online, and also did homework number 6. Okay, question 5 and question 6. So now I will also do homework number 2.
Okay.
Okay.
Okay. Thank you.
Now be careful with the homework. Okay, apply the technique that I teach you, then check the final answer. Okay, don't copy exactly what they do. Why? Because when they were doing their problem, they don't know any of these rules that I'm writing for you.
Okay.
Okay, so don't look at their final answer. Don't look at their working. Are we clear?
Makes sense.
Okay, thank you. Okay, so that's why the solution is a double-edged weapon. It can make you more confused. Right. So now let's do this. Okay, without the equation. Okay, I make you form the equation because I'm still teaching. Okay, I want you to learn more. Okay, so that's why now you see it answers to you once I start doing the distribution. Okay, we see that y alpha at point A, you have point alpha, and you have alpha value, you have beta value. We calculate the beta value, and you can see at point A there are two answers. Okay, there are two shear stress, but you compute the higher shearing stress. Okay,
Sir, why is it so though? Like at point A, we have multiple values of
this is because over here the thickness is what, 160, yes or no, for the flange,
yeah,
right? And the formula is shear is equal to VQ divided by I what, T,
hmm,
right? At point A, there is a boundary between 0.16 and what? Twice of what? 20 millimeters. That's why you have a step function.
right, okay,
Okay, so that's why you have two values down here. So for every of this is for every time you see shearing stress, if you have different thickness, this is very unique. Okay, yeah, this is very unique. You always will see this, right? So now let's do this problem, right? Let's do this problem without the without the blah, without the what I'm going to say now. Yeah, without the distribution. Okay, let's do it without. So we're going to find the shearing stress at point A. Okay, the shearing stress at point A. Right, shearing stress at point A, and then we know that we are going to identify shear XY at point A. This is equal to By over Q IZZ QZ divided by T. Okay, so we know the easiest thing to do is write down what we know. We know that Vy is a constant regardless of the point that we are trying to identify. So this is equal to 30 times 10 to the power 3. And then we have IZZ, okay, Newton. And then you have IZZ will be equal to IZZ is equal to what? Wait. IZZ is equal to 5.8133 times 10 to the power minus 6. Okay, so 5 times 10 to the power minus 6 meter to the 4. Now thickness, okay, T is equal to what? So T now, because the stress is going to go share between left and right, so thickness is equal to twice times by 0.02. Okay, so this is equal to 0.0. I'll just put twice times by 0.02. So later on we put in, we know that is the left and right. So from here we find our QZ, right? So QZ at point A, right? So it is, we have to consider what? This area. Okay. So this will be equal to A multiplied by Y bar. So they are constant numbers now. So the width is 0.16. The thickness is 0.02. And the distance from the centroid, so from here to here, so this is our centroid. The green line that I'm going to draw is a centroid. Sorry, I can be, I'm partial colorblind. Okay, if this is not green, you tell me. Okay, right? So the distance from here to here, right? So we know that this is 10 millimeters. The whole thing is 35 millimeters. So the distance from the green, the in between the green, this is equal to 25 millimeters, right? So it's equal to 0.035 minus by 0.01. Okay, so this is equal to 0.035 1 times 0.02 times 0.16. So it's equal to 80 times 10 to the power minus 6 meter cube. So therefore, the shear XY at point A is equal to V is equal to 90 times 10 to the power 3. Q is 80 times 10 to the power minus 6. I is 5 divided by 5.8133 times 10 to the power minus 6. And the thickness twice because of left and right divided by 0.02. Okay. So this will be equal to 90, 80 times minus 65 point divided by 5.8133 power minus 6 divided by 2 divided by 0.02. So this is equal to 30.963 times 10 to the power 6 Pascal. Okay, I hope it's the same. Okay, I really do. Okay, so if you look over here, why? Okay, if you look over here, what was the answer? 30.963. And what do we get over here? 30.963. Okay, right. So if you use this equation over here, right? If you use this equation, so if you use this equation, you have to use the what? You have to use this function over here. Okay, you have to use this function over here. You don't use this function because this function, the thickness is equal to what? 0.16. Whereas this equation over here, the bottom one, the thickness is equal to twice of 0.02. So if we put our y at point A, the distance from here to here, right? Distance from here to here is what? 0.15, sorry, 0.015, right? So if you substitute this expression over here, right, it's going to be looking a bit messy, but so if shear XY at point A, right, so this will be equal to 32.705 times 10 to the power 6 minus by 7.7409. Oh, I did that already. No one tell me about it, you cheeky sort. Sorry, I did that already. Okay, it's the same thing. I did that down here. Sorry. Okay, I did that down here. The answer is the what? It's the same. I have to wake up today. Sincerely apologize. Okay. Right. So now I'm going to do the same thing, and we're going to look at the shearing stress at point B. Okay, assuming that we again don't have the distribution equation. Okay.
Eugene, just before we go on, I do have one question though.
Yes. Yes.
So if point A were up somewhere in the flange.
Ah, yeah. So if that's the case, I like that question. If point A is here, right? Then the equation you have to use is the flange equation. Make sense?
Yes. So when we're using the shear stress equation, then would all the values be the same, but just the t is different?
Repeat your question.
if when we're using the shear force or shear stress equation, would all the values we're putting in it be the same, but only the T would be different then? Because we're using the Q from the flange anyway?
So you're talking about the flange, right? Not the web, right?
Correct.
Yeah. Just use the flange equation because the thickness is constant, right?
Okay.
Okay. Wei Ming is my busy customer. One more question. Yes, sir. When we get the reaction force, do we always choose the maximum force if the question asks for the maximum shear? So what Wei Ming asks is, let's say you have a distribution like this, right? So the thing about point N, down here we know the distance is 0.06, and you can see N at any distance, the value is at what? 80. Okay. Now, what if, based on your quiz, right? This is your quiz question, right? That is the distribution of your shear stress. Okay, that's the distribution of shear stress. So this is what was given. Now, all the quiz that I gave you so far, the questions are from PO exams. Okay, they're all PO exams. Okay, and it's what you can see that it's easier than what I'm teaching you, I hope. Okay, right? They never ask for distribution. It's so straightforward. Yeah, because PO is minimum standard. I'm going for maximum standard. Okay, I don't want to do minimum for you. So over here, right, the shear stress is constant up to here, right? And then beyond that is no more constant. So if a question were to ask like this, then you have to know about this distribution. Okay, so if let's say the position of interest, is somewhere around here, then you have to compute what is this value. Are we clear? Wei Ming, okay, is that clear to you? Okay, so it all depends on the point of interest where the question asks you, or you calculate where the maximum is.
So Eugene, good to know this, because the way that I did it was basically a step function, because I just used the concentrated value.
It's okay. Don't worry about it. Okay. So I want you to look at how this is solved, and the most important thing is to find your what? Your Vmax. Okay. So that's why this figure is so important. You have to sketch your what? Your Vmax. Okay. That's the most critical, because down here you can pick any values. It can be 54.25 or 75.75. You pick 75.75. Okay, you pick the highest value. But if some questions are very specific, they want it to a certain distance, like 2 meters from the extreme end, then you have to address exactly where of interest. Are we clear? Okay,
Yeah,
but in general practice, yes, you will always calculate where the shearing stress is at maximum. Okay.
Okay.
Right.
Sorry. I actually had another question, because in that particular quiz question.
Can we do the quiz later? I'm in a bit of rush because I have a lot to cover, and I already posted the solution. Can you review the solution? Then anything that all of you don't understand can come back to me.
It was just about point E, but okay.
Okay, so come back to me if you don't understand that point, because as I said, I have a lot to cover today. We might go on to 12:30 again. Okay, right. So now we're going to do at point B. Okay, we're going to do at point B. So at point B, remember when last week I taught you guys, right? At point B, it can be confusing without those rules, right? It can be confusing without those rules. So this is where our centroid is. It is just a sketch, right? And then this distance from here to here is equal to 0.035 meters, right? Now the area of the point of interest is at point B, right? So based on the rules that we've created, right? So remember, we drew this, right? Last week we drew this, right? I make you guys think about this, right? Where was it? Or was it one of these example? Right? We did this, yes or no? right? I ask you, if I want to find point beta, which area of region that we're going to choose, okay? So we don't cover the top like this. So the first moment of area cannot cross the what? Cannot cross the centroid, right? So down here we know that, okay, the first moment of area cannot cross the centroid. So if you think that this is where your Vy is, right?